Okay, good evening everyone, and thanks for joining us. Tonight we have very interesting lecture by our former colleague Aleksandra Ćiprijanović, now working as a Wilson Fellow Associate Scientist at Fermilab, and she will talk about bridging the gap between simulated and real data with artificial intelligence. So, Aleksandra, go on.
Thank you. Thanks for the invite. I'm super happy to be able to present back in Serbia, although, of course, a bit sad that it's not in person, but hopefully soon it will be again. I am currently at Fermilab. In the data science simulation and learning division. Most of my projects that I work on are astrophysics and cosmology related, but not like completely exclusively astro. I'm also leading the cosmic AI group, and I also have a joint appointment with UChicago, and so I can like work with students over there. So I'm planning to tell you about a topic that's very like near and dear to my heart. And I also think that this problem that I'm going to talk about is definitely much more far-reaching than astrophysics and cosmology or any kind of research that we're directly involved in, because it's a problem of domain shifts in scientific data sets, and I will tell you what this actually means, and development of AI models that are going to try to overcome this domain shift problem. But before I go on to like telling you about what is domain shift, what is domain adaptation, I kind of want to mention this because I feel like this is a good segue into the problem. So the reason why, one of the reasons why AI is becoming so popular in recent years is definitely the data set sizes and complexities in astrophysics and beyond. So Fermilab, for example, is particle physics lab, accelerator lab. So we have, on top of of course, the astro and cosmology research, we have other big experiments focusing on different types of high energy and particle physics topics. So here I'm just giving 3 different examples. Of course, to us, the most well-known is Rubin LSST, so astrophysics and astronomy survey. And the plan, at least for Rubin, is to have around 20 terabytes of data per day. And of course, as you all know, the plan is to run for 10 years. So it's going to be petabytes of data by the end of the final data release. So obviously, even the simplest tasks that we need to do with this sort of data set sizes are becoming challenging, even just storing them or moving them around, let alone actually doing science with it. The other 2 examples that I want to show are probably even worse. So one of them is Dune. It's one of the biggest, it is the biggest neutrino experiment currently being built. It's going to be led by Fermilab. And this neutrino detector is going to produce around 30 to 60 petabytes of raw data per year. And more interestingly for us, for example, they will also have a different kind of scanning mode where they will try to detect supernovae explosions. And in this case, because the flux is going to change quickly, you will basically generate even more data. So a few hundreds of terabytes per month in this kind of mode. So even worse than the regular neutrino detection mode. And then the final example I want to show you is the upgrade for the LHC at CERN. So it's called the high luminosity LHC. And I mean, their dataset sizes are already crazy, but the plan when they start actually running in this new mode is going to be around 650 petabytes per year. So basically, all of these different groups really need AI in some sense for many different types of problems. So for example, let me see. So even data handling and decision making, especially if you need to do any kind of real-time decision making in astronomy, that can of course be translated to alert systems. So if you have a supernova or something else that's like really quickly changing, you need to be able to find it in time and alert other telescopes so that we can observe it at other wavelengths. But on the other side, on the particle physics experiments, you, of course, if you're looking for something weird, that happens very rarely, and you need to be able to recognize something is weird or not. For them is also even more important because telescopes tend to keep all of the data. So whatever we observe, we save everything. But with like particle accelerators and other big experiments, there is so much data, and most of the data is not really needed. It's not what they're looking for. So they actually need to be able to decide what to save, what not to save. And of course, this is something that should be decided in real time. So overall, like automated experiments are something that in the future we would really like to have. Yes, and of course, the most basic thing is working with big data sets later on in the process of doing science with catalogs. Even that is, as the data sets increase and the complexity increases, is becoming, of course, more challenging. So hopefully, like, we really do need help with all of these aspects of scientific work. And AI is proving to be quite good at solving many of these problems. Of course, we have a lot more developing to do, but it's definitely helping us already perform some of these tasks. So basically, this is kind of the outline of my talk, the thing that I want to talk about. So, okay, AI is great in some sense, but it's like we've been chatting before the seminar, it does come with its own set of challenges and problems. And one of those problems is domain shift. So I'm going to tell you what that is. And then I'm going to introduce a specific type of AI methods called domain adaptation. And tell you a little bit about that, show you some examples. I'm also going to talk about overall AI model robustness and some other problems that might arise when training AI models for astrophysics, and then finally show you some like universal domain adaptation methods that we've been developing recently. And actually that paper is officially published and is public today. So I just received this morning a link with a DOI number. So anyway, I'll have links for all of that if you're interested, and we can chat later as well. So, okay, domain shift problems. What are domain shift problems? So domain shift or dataset shift. So, okay. So if you have questions, please feel free to stop me, but somebody is unmuted and then I can hear my echo. Okay, I think it's fine now. Okay, so when training AI algorithms, especially the most common type of supervised learning algorithms, the model learns usually by having a lot of labeled examples. So you need to have pairs of, for example, images or any kind of like other data product that is linked to some property, whether that is a class or some numbers describing the thing that you're seeing in the image. This is how the most commonly methods are trained. So obviously, this means that in science, you should have very like trustworthy data sets with labels that you really believe in. That's not always the case with real data. So many types of studies start from simulated data sets or maybe some old data that we know very well. And we want to try to train an AI model to perform some task on a new data set. So again, the most basic example here would be we want to start training on simulations, but we want the model to work on real data. And here I just have two different examples of, again, one of the old neutrino detectors, microboon, again here at Fermilab, where we have simulated event of neutrino going into the detector and decaying, and a real event. And on bottom, you have just some simulated illustrious TNG galaxies and a pair of real merging galaxies. So obviously, even by just looking at them, the differences are kind of obvious in this case, but the differences can be smaller and maybe not visible to us, but they usually are there. So in between simulations and real data, differences can come from either missing or unknown physics that is not part of our simulation, or maybe the geometry of the problem is slightly wrong, especially, for example, in particle physics simulations, or the background levels are not particularly correct in the simulation. Or maybe even if you do know everything very well, you still need to make all kinds of approximations or tricks in the simulation because of the computational constraints, so that the model just runs in reasonable amount of time. And this makes the final simulation slightly different, of course, than the real data. On top of that, you can have all kinds of detector problems or transient phenomena, or I don't know, pixels in your CCD are not working properly, or maybe you have some correlated noise in the pixels that is not, of course, included in your simulation, where you're simulating maybe just Poisson noise or something like that. So imperfect addition of these observational effects on top of the simulation can also cause problems. And as I mentioned before, of course, you can just have a situation where you are not using simulations, but you have two different detectors. And I'm going to talk about that at the end of my talk. We have two detectors, so two telescopes. And in that case, everything is different. But you still want to have a model that works on both, right? Because it's observations of the same universe. You need to have a model that can work on both data sets. So again, I'm not going to go too much into the how AI models are trained. So if you have questions about that, please stop me. I have some backup slides to show you. So, but here is just a super simplified version of how a model is trained. So let's imagine that I have a very simple task. I want to classify, for example, merging and non-merging galaxies, and I have these simulated images from Illustris. And of course, they are labeled because they're from simulation. I show my model a bunch of these with labels. It learns how these galaxies look like, so extracts useful features. And for example, here in the middle, you can see that this model, for example, picked the peripheries of galaxies. So the pixels on the periphery are brighter. It means that it finds these pixels more important for classification into a merger class. So it found that a symmetric, interesting behavior on the periphery can be a sign of a merging galaxy. And so we use these features then to classify images. And then, of course, in the testing phase, once you show it another unknown image from the same data set, it knows how to handle it. But if you show it a noisier version, so let's say that this is an observational image, so observed image with observational noise, it doesn't know what to do because this galaxy just looks very different than what it is trained on. So why does this happen? So when you build a model to do any kind of task, so in this case, it has two classes, and it builds a internal latent space view of your data set. So within the model, you have its own internal latent space. It can be arbitrarily dimensional, depends how you build your model, from a few dimensions to thousands. And it tries to place similar looking objects in similar locations such that you have a decision boundary between them, and you can distinguish if a new object is located on one side or the other, and hence you can classify it correctly. When you get a new data set that has slightly different properties, this data set is not translated correctly into the latent space of the model. And so all of a sudden you have either slightly shifted situation, or it can be completely mixed or randomly placed. And obviously the old decision boundary doesn't work anymore. So the solution is to somehow align the data sets, so all the new data, such that the correct class is on top of the correct class, and you can build a common decision boundary, and hence the model will then work in both domains. So how do you do that? Well, domain adaptation. So that is the group of methods that are kind of trying to deal with this problem. The aim of all of these methods is basically to try to find more robust features in the images, if we're working with images, and these features are domain invariant. So find something that is useful, but that is present in both data sets, and build the latent space just using these domain invariant features. So this is a very common problem outside of science too, of course, like in industry. If you're training a self-driving car on the streets of Belgrade, and then you want your model and your car to work equally well, I don't know, in Norway, where the people are dressed differently, everything is under snow, and so things like this, and small changes, but they are enough for the car to just not work properly on those streets. So luckily for us, that means that a lot of people are thinking about this problem. And overall, I like dividing these methods into two different approaches: distance-based methods and adversarial methods. And I'll show you like really brief examples of both. But overall, the training is modified in such a way that on top of the regular, what I call a task loss, so loss function that is being minimized to perform a task like classifying galaxy images, you add on top of that extra domain adaptation loss to allow the model to learn domain invariant features instead of the regular ones, the most obvious ones. And more importantly, and why these methods are so important, is that these methods can be built even when your target domain, so for example, real observations, are unlabeled. In many cases, many methods just work with unlabeled data. So that means that you can modify the model to perform on completely new observations that you just got. So maybe like LSST first light, you can already modify your simulated data, model trained on simulations to perform well on new unlabeled data sets. If you had labels, of course, you wouldn't need to do all of this gymnastics. You could just train on the new labeled data set. But again, often we're not that lucky. So the type of methods that I like to start from are domain adversarial neural networks, or adversarial methods. This is just one of them, because it's, I don't know, for me, the most straightforward to understand, and I like kind of describing this first. So in this kind of setting, you have a model that has three parts. The green part here extracts useful features. So it has these 2D convolutional layers that extract interesting information from the images. And once you summarize that into this 1D green part, which is the latent space of the model, you perform two tasks. You have two branches. The top branch here, the blue one, is doing classification. So it outputs, in our case, in the example before, merging and non-merging galaxy class. So it learns to distinguish between galaxy classes. This other part is trying to classify the domains. So it's going to try to classify if the image is coming from simulated data or from real data. The trick here is this gradient reversal layer. So the gradients that flow into this section here actually are reversed, which leads to this loss, the domain adaptation loss, to increase over time. So what does this mean? This means that over time, as the model is improving, as the model is training, the branch that classifies galaxies improves, and it becomes better and better at doing this. But the branch that's doing classification of the domains is supposed to become worse and worse. What does that mean? It means that the features extracted in this first green part, they need to be very useful for classifying galaxies, but completely useless for classifying the domains. So that means that you're literally finding domain invariant features, features that show how galaxies look like, but they're present in both data sets. And that's how you kind of get these domain invariant features. The other method, the distance-based methods, are based on having a metric that describe how similar these two distributions are and trying to minimize it. So one example of such method is maximum mean discrepancy, or MMD. So let's say that we have these two distributions, P and Q, blue and red. And these are the latent space versions of our data sets. So how our AI model sees the data? You don't know how these look like, but you want to be able to compare them. You can only sample individual points from them. So you can just see where individual images are located. So what you do is you substitute every data point with a kernel. So for simplicity, it's a Gaussian kernel, but it can be a mix of whatever kind of kernel you like, and combinations of kernels are still kernels. So you can do that easily. And you sum them all up. You get this final blue and red curve, for example. So let's say that if we sum them all up and we create this witness function, which is the mean of this sum minus the mean of the other one, you get this black curve. It's obvious from this plot that if you try to minimize this witness function over time, that means that the blue and red curves are going to become more and more similar. So ideally, they will be identical and the witness function is 0. So what that basically means, so this is basically just the whole equation that gets minimized as a loss function. So you have sums of kernels in blue. So blue kernels show you the similarity between individual data points from the blue domain. The red one is for the red domain, and you have this cross similarity. So basically you have this matrix that has all of the possible combinations. And on the diagonal, you have, of course, blue, blue, and red, red, or I don't know, here, dog and fish examples of similarities. And you have off-diagonal elements that are dog-fish similarities. So obviously from this equation, the dog-fish similarities are the only ones with a negative sign in front. So if you maximize this last term, so if you maximize the similarity between dogs and fish, you will minimize this loss function. So basically you're trying to find a way to see the dog and fish as similar as possible. So in practice, how does that work? So now instead of just having simulated images with labels, I also add observed images without labels. I don't need them for labels. They're just there to allow the model to find what is similar between the data sets. So the model actually switches from having to look at the peripheries to look in the center of the galaxy. And obviously in this case, that is more than obvious why this is needed, because the centers are the brightest points that remain after you add the noise. So in the testing phase, then you get a model that can perform well on both data sets. And this is what we want. So another example of how the latent space actually looks like, so because I want to kind of better describe what I was talking about. So here is an example where, again, on the left, I have a couple of examples of simulated illustrious merging galaxies, and on the right, I have real merging galaxies from SDSS. They were labeled by the Galaxy Zoo volunteers. So obviously, they're quite different, especially because the Galaxy Zoo will have usually mostly just very easy examples because people needed to label them. So you get high certainty only for obvious examples. So here, this bottom plot shows you a 2D version of the latent space of the model. So this is before any training. So the two classes, merging and non-merging, are blue and red. And examples from the simulated domain are these kind of see-through data points. And the other, like the brighter ones, are the observations. So before any training, of course, all of the classes are mixed. And also, you can already see that the model translated them into two different regions in the space. So if I just do regular training on the source domain, on the images that are from simulation, the model again, so the top row here in this blue-green part, the top row shows which pixels are important for merging class. It's again the periphery. And for the non-mergers, the model usually values the centers more. Again, makes sense. Non-mergers are usually just regular small dots in the center of the image. So the latent space after training looks something like this. So blue and red have started to distinguish. And the accuracy around 80%. Don't remember exactly how much, but it was above 80, which is pretty decent for this sort of problem. But the real observations are completely kind of messed up. You see like the behavior flips, and you can see all kinds of random behavior here. And that is because you see where it is. It's still detached, it's still mixed, and the accuracy is 50%. If instead of doing this, you actually train with domain adaptation, so either maybe that adversarial method or the MMD and distance methods, you get a similar behavior in the source, but you get similar behavior in the target also. And this is how the latent space now looks like. So now both domains are on top of each other, and you have blue and red that are distinguished, and the accuracy, of course, is large now in both domains, which is what we want. Okay, so with this, I actually want to move on to a different problem, which is a little bit related to this, but definitely the method that I'm using is related. But so I just kind of wanted to talk about this problem too, because I don't think that we are talking about this that enough, at least in astronomy. So the problem is what happens to our AI models when you get some kind of inadvertent data perturbation. So especially when working with images, perturbations are something that we should expect, not think that that's going to happen rarely. If nothing else, because of compressing and decompressing data. Data compression is not always lossless. And when you zip a file and unzip it, your image might have some pixel that actually ends up being slightly different. On top of that, you can, of course, introduce your own set of problems by, like, I don't know, not pre-processing data nicely, having a cosmic ray that you didn't remove, having some transient phenomena that's like astrophysical in nature, but that you didn't account for, and so on. And in industry, we know about this problem. I mean, it's been mentioned quite a lot because of the adversarial attacks. So here is an example of that. You have an image of a pig, and you add this very small noise to the image that ends up like not really changing the image. Like you can't see any difference in this final image, but the class changed from pig to airliner with very high probability. So things like this can mess up your model quite substantially, even completely. And the worst part of it is that not even like you can cause the same problem with just 1 pixel or 2 or 3 pixels that are changed. And we can always assume that in astronomy, we might have a pixel somewhere that is, for some reason, changed. And it doesn't even have to be changed in a very weird way. So for example, if your pixels are from 0 to 1 in value, you normalize your images, you can have a pixel that is in the same range, but that is just very unluckily placed in the image, and you can cause this sort of problem. So what we need to think about is how to build models that are robust to see these sort of weird situations. So what I wanted to see is if I have LSST mock data. So for example, in this case, I'm making, again, galaxies, and I have spiral, elliptical, and merging as 3 classes. If I make a year 10 mock, can I perturb a single pixel in a not weird way, so just like regularly perturb it? Can I easily do that, and can I make the model that knows how to classify galaxies perform incorrectly? And ultimately, if I can we use all the data, like year 1 data, that is noisier, to help us build a more robust model that understands that maybe noise levels can be different, and this weird like noise stuff is not related to the galaxy. So here's another plot that shows you how the AI model internally sees the data. So these plots are called church window plots. They show you, again, a 2D version of the latent space of the model, and these colored regions show you the regions where the model places specific type of class, so after training. So obviously you can see here, like I have 3 classes. And let's take one image of a spiral galaxy, this X here, and let's see where it is. So this is a year 10 spiral galaxy correctly classified. If I find the same exact example in the noisy version year 1 data, it ends up being here. So it moved to the merger class. And this is only because the noise is higher in this image. Obviously, you could have expected this because this is the whole topic. Like, of course, matter. So the regular trained model makes a mistake here. In this middle image, in the X, to perturb, X, to perturb, I can easily do that. I actually can easily flip it to cross to the elliptical class. So if you look at, again, a similar plot like before, which is called TSNE or isomap, depends, like there are different methods of plotting this. You can see that the was trained on year 10. So these are the field circles. They have 3 classes. So this is the data set that the model was trained on. The year 1 noisy version are the empty circles, and they're mostly here. And that's why, of course, the star on the left is in the merger class, as most of the other examples. So you can see, again, the triplet of images on the right, too. So if I now try to, again, use domain adaptation, but for a different purpose, now I want to use the domain adaptation to increase robustness and hopefully solve the problem of the 1-pixel attack and of the noise levels and everything. So I now want to use old data, so this noisy year 1 data set, to serve as an additional data set to find domain invariant features that care less about the noise levels. This is what I get. So in this case, both field and empty circles, you can see that they have like 3 groups. You have 3 classes. And you can also see that because of that, the star, which is the noisy version of my X, of my spiral galaxy, is in the correct place. And overall, the accuracy, of course, for the noisy data increased tremendously, but that is to be expected because this is domain adaptation applied to it. But the thing that I want to mention is this triangle. So the triangle is the 1-pixel attacked image. It is still in the wrong class, but this is because I'm trying to find this pixel. So I managed to find it, but it was definitely a lot harder to do that. So we couldn't find correct pixels to perturb for all images, which was very easy before. And the second thing is that for those that we were able to flip in the incorrect class, the distance to them in the latent space increased more than 2 times. What does this mean? This means that using domain adaptation allows you to increase the distance between the classes so that small perturbations, even though they're going to move your image around in the latent space, are a lot less likely to cause it to jump to the wrong side. So with this, you're not only allowing the model to work on multiple data sets, but you're also allowing it to be more stable on these sort of inadvertent perturbations that we might like not really know where they're gonna come from, so we can't like defend against them in a planned way. Okay, and with that, I wanna just show you something more universal and like our solution to an even more complicated problem that we've been working on recently. So this more complicated problem is what happens if I want to bridge different observational data sets. So what if I don't even want to use simulations? Or maybe I do, but I also want to have multiple observational data sets. And I want to be able to go from, for example, SDSS that we have had for years now and know very well. And we want to build models on this data, but we want to apply it to dark energy survey, to LSST, to whatever else. So in this case, as I mentioned before, you have a much greater difference between the data sets and hence much bigger gap to bridge across. So the noise levels, the PSF is different in this case, the pixel scale is different, the depth of the survey is different. So even the data, like the object distributions are going to be different, or the magnitude limit and how faint of an object you can observe. So all of these things cause additional problems for the model. So how do we build something that's universal? On top of all of that, there are different types of like data set overlaps that we have to like carefully think about. So here I have a couple of examples. So again, source domain are is the solid line and filled shapes, and the target domain is the dashed line and empty shapes. So the most simple problem is when you have, if you're doing classification, of course, you have the same classes in both data sets, everything overlaps. You just need to be able to align the correct stuff on top of each other. Okay, this is the closed domain adaptation problem. This is the simple problem. But you can have extra classes in the source domain, which we call partial domain adaptation problem. In this case, it's not that hard because this is a labeled data set, so you can kind of know. Although you might not know that there is, this class is actually missing in the unlabeled data, so that's why the problem is hard. The worst part is when you have an open domain adaptation problem, when you have extra stuff in the new unlabeled data set, or you can, of course, have extra classes and extra objects in both domains. So to have a model that works in both, you need to be able to find the things that do overlap and try to align only these objects and not try to align the things that are not overlapping. Otherwise, you will either not be able to overlap things at all, or you will suboptimally do it, and hence the model will not again perform ideally. So the solution for this could be to use self-supervision. So instead of relying on explicitly writing a loss function like that MMD distance or some kind of other distance, so something that we really want to minimize, instead of doing that, we allow the model to just look through the data, find what is similar, and align things more flexibly without the need to minimize any kind of explicit function. So this is what we try to do. And yeah, in this paper that I guess was published today, we handle 3 different problems. So we handle a problem of 2 data releases, so LSST mocks from year 1 to year 10. So how to build a model that is updated and works whenever you get a new data release. And then different surveys like SDSS and DCALs. So again, all to new data. Or wide and deep fields of the same survey. So we use data from the regular SDSS wide field and Stripe 82 deep field. So yeah, and I'm gonna show you results for the middle one, across survey. And we also wanted to do it more complicated. So we added, we wanted to have more classes, basically to start and test with the just more complicated problem. So we're pretending that we have 9 known classes. You can see them here. They're different like subgroups of galaxies, galaxy morphology. And then we also want to test the hard case of open domain adaptation, where we actually add an extra class in the unlabeled target domain, which is in this case decals. So in that case, we add a strong gravitational lens class into the unlabeled data. So this does not exist in SDSS dataset that we made. So we want to see if we know how we can make a model to align this and also to be able to handle the gravitational lens class. So here are some examples of just how the data looks like. Yeah, we have 9 classes on top, 10 classes in the bottom, and the top 2 rows are some like correctly classified examples. So you can see here in the top 2 lenses that we found. But anyway, how do we do this? We do this by having 3 different loss functions that have 3 different tasks. And all of them perform on, they work all of its magic on the output of the neural network. So this is a 10 class vector that is predictions for each of the classes. So yeah, so you have outputs from 0 to 9. These are your 10 classes, and you have some numbers that the predictor spits out for all of these classes. And this is the numbers that we want to look at. So the first thing is what to do with labeled stuff that we know. So the source domain, again, the same labeling, filled circles, filled triangles is the source domain. The solid line is the source domain. So these are labeled data sets. So we can easily just do whatever you usually do for classification, which is in this case cross-entropy laws. So it's basically this where you have predicted labels, these y caps, and true labels here y, and the weights that are there for each class, because we want to be able to handle imbalanced classes, so have a weight to weigh stronger predictions for a small class so that the model doesn't ignore a small class. But this is just a regular routine stuff. So what do we do with those classes that exist in the target domain but that are not labeled? Well, this is done by self-supervision. It's actually inspired by something called contrastive learning, just if you want to Google that in the future. So it's a method where you kind of switch from regular task of classifying galaxies into a new task. So because the model doesn't have any labels, the new task in this case is going to be, are these two galaxies images similar looking by any kind of property that you can extract? So what is the model is actually using is a similarity label instead of a galaxy label. So similarity label S, which means if the two galaxies are similar, the similarity between them is 1. If they're not, the similarity between them is 0. And to find that similarity label, we basically look at the output and we say, let's rank order these outputs. And if the two images, for example, have the first 5 largest output values the same, that means that the model probably thinks they are similar enough, and then they get a similarity label of 1. And there is also a bank that just kind of stores information for all of the images so that you can compare all of the galaxies from source and all of the galaxies from target and basically align all of them. But the final thing is, what do we do with the extra class? So this extra class is, of course, not going to be aligned here because it will look different. But we actually want to be able to push it away even further so that it doesn't mess up the domain alignment. So for that, we actually use entropy of the output vector. So if the model sees something familiar, it will usually have very low entropy in this number. So it will just give you a large number for one class or maybe a few more. But if it sees something very weird, you're just going to have a lot of numbers that are large in all of these buckets. So the entropy is large. So what we want to do is find those that have large entropy and push them even further away. And let me show you how this works. So yeah, the final loss is just a combination of these 3 terms. And here's an example. So I'm plotting 2 known classes, bar spiral and round smooth. Again, source are filled shapes, target are empty. And in the target, I'm also adding the lens, the unknown extra class. So no domain adaptation, things look kind of crazy. With domain adaptation, in this sort of flexible way, we call it DeepAstroUDA or universal domain adaptation, you have the known 2 classes on top of each other, but also more importantly, well, I guess equally importantly, is that the merger class is pushed to the side. So it's not trying to align it with the other known stuff, which would be detrimental in this case. So if we look at the predicted versus true outputs, you can see that mostly it's predicting the correct class every time. 0 and 1 are kind of mixed because these 2 classes are actually disturbed in merging galaxies. So they truly are similar looking. And so this is actually for us another proof that the model really understands how galaxies look like, because these 2 should really be confused. And this is also, so here on the left, even cooler plot, which is the accuracy of known and unknown classes in the target domain. So all of the known classes, the 9 ones, are the blue line. So it's pretty good. It's around above 80%, again, for galaxy morphology. Nice. But the model is even higher in accuracy for the lens class. So it doesn't know what lens is. It hasn't seen any lens labels ever. But it definitely knows that it does not look like all of the other stuff. So not only we're able to bridge the gap between observations, we're also able to find interesting new data that is not contained in our old catalog. So in this case, these are, for example, lenses. And here are some example lenses that were found in the decals data with this method. Okay, so yeah, I will stop here. I hope that I kind of covered what this method these methods actually can do. So bridging between simulations and observations, increasing robustness to data perturbations, help you bridge the gap between different data releases or surveys or wide and deep fields. And with our group, we're like applying them to all kinds of different problems. So you'll soon have be able to see like some papers related to strong gravitational lensing, cosmology, and galaxy properties. So not really classification, but like inferring, I don't know, star formation rates, stellar masses, other stuff, or more detailed merging galaxy properties. So yeah, these are proving to be very useful. So we're kind of excited to apply them in different problems. Since, yeah, kind of every study more or less has this problem. So this would not happen without all of these people that I collaborate with, and this is just a small part. Of course, most of them are from Fermilab in Chicago, but there are other labs, Lolek, Argonne, Oak Ridge, Berkeley, or Space Telescope Science Institute. Yeah, and finally, if you're interested in AI for astrophysics, I want to advertise Deep Skies Lab, which is basically just a very active Slack, but it's a very good community of people doing AI for astro all over the world. So I definitely invite you to join this group if you're interested about that. Yes, and with that, I will stop. Thank you.
Okay,